This video, we're going to visualize those results from the last video. In the last video, we found the slope of the graph of the curve given by r equals 1 minus sine of theta at pi over 4. And we also found points of horizontal tangency and points of vertical tangency, and points where the derivative dy dx was undefined. So these were all the values that we found. We determined that at pi over 4, the slope of the graph was square root of 2 minus 1, which is about 0.4. And then we found these points of horizontal tangency and these points of vertical tangency. And y prime of theta and x prime of theta were both 0 at these locations. So those are points where dy dx is undefined, or undefined using that formula that we looked at earlier. But I wanted to be able to visualize all of this. So I told you this should represent a horizontal tangent line, that should represent a vertical tangent line, and I'm not really sure what's going on here. And then we've got the slope of the tangent at theta equals pi over 4 is this, but we didn't actually get to see it. So in this video, what we're going to do is graph r equals 1 minus sine of theta. Because we've already made a video where we graph an equation like this, or we graph a polar equation, I've written out some of the steps in advance. So remember how we do this. The first thing we do, if we want to graph r equals 1 minus sine of theta, is we graph the curve in the r theta plane. So this is just the sine function. It's flipped upside down because it's multiplied by -1. So instead of going up first and then down, it goes down first and then up. And then we added 1 to it, so it raised the whole graph up 1 unit. So this is what the graph looks like. With this graph, I can make a table of values that will allow me to graph the curve in the polar plane. Now, to come up with this table of values, the first thing I did was I computed the increment. In order to get a nice collection of points for my graph, I like to use 1/8 of the period as my increment. The period of this function is just 2 pi because there's nothing multiplying that theta. So if I take 2 pi and I divide it by 8, I get pi over 4. So I made a table of values, and at each value of theta, all those multiples of pi over 4 between 0 and 2 pi, I found the resulting values of r. Now, if this looks tedious, try not to think of it as tedious. I'm not literally just plugging this into this function over and over again. I'm using some nice properties of the sine function. I know my graph looks like this. So at multiples of 1/4 of the period, so at 0, pi over 2, pi, 3 pi over 2, and 2 pi, I know we're going to be at these points on the graph. I'm going to start at that middle line. Because it's a negative sine function, we go to our min, then we go back to the middle line, then we go to the max, and then we go back to the middle line. Since that middle line is y equals 1, we go 1, down to 0, then back to 1, then up to 2, then back to 1. And then because of symmetry, when I'm finding this point here, I'm also finding this point here. So this value is given by 1 minus sine of pi over 4, and sine of pi over 4 is square root of 2 over 2. So I simplify that and I get 0.3. Well, that is also 0.3 because of symmetry. Then over here, instead of subtracting pi over 2, or square root of 2 over 2, I'm adding square root of 2 over 2. And so I get this value, and that one's the same. So I fill in the table pretty quickly, and now I've got this table. And that will allow me to graph the function, or graph this equation, excuse me, on the polar plotting paper. So let's do that, and then we'll look at the points of tangency listed below. So when theta equals 0, r equals 1, and the largest r ever gets to be on this table is 2. So I'm going to make my r these little subdivisions count for more. So I'll say that this is r equals 1 right here. And that's 1, 2, 3, 4 units out. And then this will be r equals 2. Okay, so we go to the theta equals 0 line and go 1 unit out. That's a point on our graph. Then on the pi over 4 line, we should go about 0.3 units out. A pi over 4 is the same as 45 degrees. So if this is 1, 0.3, that's going to be 0.25. It's going to be a little bit, this is 0.25 and that's 0.5. So it's about here. Oops, that's 1. That shouldn't be on the graph. This is on the graph and that's on the graph. Okay. And then at pi over 2, we get 0. So we're at what used to be the origin, which is now called the pole. Then at 3 pi over 4, that's 135 degrees, we go out 0.3 units. So we're on this line. We go out 0.3 units to here. Then at pi, r is equal to 1. So go in the direction of pi, 1 unit out. Okay. Then at 5 pi over 4, we go 1.7 units out. 5 pi over 4 is the same as 225 degrees. So this is 1, that was 2, and we said about 1.7. So 1.75 is there, so it's just a little bit less than that. Okay, and then at 3 pi over 2, r is 2. So we're on the 3 pi over 2 line, and we go 2 units out. So there's 1, there's 2. And then at 7 pi over 4, we go 1.7 units out. That's 1, that's 2, that's 1.75, so it's a little bit less than that. And then at 2 pi, we're back to 1, so we're right here. Okay, so this is what our curve looks like. Start repeating itself at that point. It's a cardioid. Looks like a heart. And I'm probably not making this as rounded as it's supposed to be. So that's roughly what we've got here. Okay, so that's the rough shape of my graph, if I've done everything correctly. And I think that point is on the wrong line. It should not be on the 300 line. It should be on the 315 line. There we go. So it should go like that. That's better. That one was wrong. Okay. This 315 is that 7 pi over 4. All right. So that's my graph, and I'd like to illustrate these guys now. We're told that we have points of horizontal tangency at r equals 1/2 and theta equals pi over 6. Now it's not going to be perfect because of the way I drew my graph. But let's see, pi over 6, well, this is pi over 12, and this is pi over 6. So at pi over 6, r is supposed to be 1/2, and r equals 1/2 would be right there. And theta is equal to pi over 6. So we're supposed to have a horizontal tangent line there. So actually that point should be on our graph. And when I look at the tangent line, it should look like that. It should be completely horizontal. And where else do I have a horizontal tangent line? at 5 pi over 6. So on the other side, at 5 pi over 6, that's over here at 150 degrees, same thing. The R value is supposed to be 1/2. Not bad. Actually got pretty close. We're supposed to have a horizontal tangent line right there. It doesn't look like a horizontal tangent line with the way I drew it, but that's because I was guesstimating so much when I was drawing all those points in between. But there's a horizontal tangent line there and there. And there's also supposed to be a horizontal tangent line at 3 pi over 2 and 2. Yeah, I think we all see that. That's at the bottom there. Yep, so I've got horizontal tangents there, there, and there. Then we found these points of vertical tangency. R is equal to 1.5, and theta is equal to 7 pi over 6 and 11 pi over 6. So let's see. 7 pi over 6 is right here. And 11 pi over 6 is right here. Okay, and R is supposed to be 1.5 on those lines. So if this is 1.5, hey, not bad, not bad. That's supposed to be 1.5. And if this is 1, that's supposed to be 1.5. Hey, pretty good, after I corrected for that 1 point that was off. All right, now we're supposed to have vertical tangent lines there. And if my graph was perfect, they would be vertical. Okay. And then at pi over 4, we're supposed to have a slope of 0.4 approximately. Let's see, at pi over 4, the slope is supposed to be small and positive. Is that right? 1 minus, or square root of 2 minus 1. It looks like it should be small and negative. Maybe I made an error on that one. I would imagine that it's sloping down, not up. Oh well. Okay, so that's how we can visualize it. Horizontal tangent, horizontal tangent, horizontal tangent, vertical tangent, vertical tangent. And that should indicate a small positive slope. Maybe there's a small, pi over 4 is right here. Yes, actually I would imagine the small positive slope right there at pi over 4. The tangent line at pi over 4 looks roughly like this. Yeah, that looks like it has a small positive slope. I was looking at the pi over 6 line. That's why I was assuming that it was the wrong sign. Okay. Now, whenever we were calculating the points of horizontal and vertical tangency, we were setting y prime equal to 0, and we we're saying, where's y prime equal to 0 when x prime isn't at these points? And that's where we had horizontal tangent lines. And then for vertical tangency, I was setting x prime equal to 0, and I was saying, where is x prime equal to 0 where y prime isn't 0? And we were at this. And then we said, okay, there are some points where x prime of theta and y prime of theta are both 0. That formula for dy dx is not defined. In those cases, theta was equal to pi over 2 plus 2 pi n. So that means we are up here at the top. Ooh, you see what the problem is? And r happened to be 0 there. So we're at these points. So the slope is not well defined. Well, sure, look at that. Of course the slope isn't well defined there. We have a little cusp. That makes sense. Now there's one other thing that will help us to graph our function. And that is calculating the tangent lines of the graph at the pole. This is a fact, and I'm about to derive it for you. Now, let theta not be a constant. It's just a particular value of theta. If r of theta naught is equal to 0, and the slope, or the derivative of r with respect to theta at theta naught is non-zero, then theta equals theta naught is tangent to the graph at the pole. Let me show you why this is true. Now remember how we came up with dy dx. We said, let's take the derivative with respect to theta of y, or y is a function of theta, and let's divide by the derivative with respect to theta of x, where x is written as a function of theta. Well, remember what y is. If we're in polar coordinates, y is r of theta times sine of theta, and x is r of theta times cosine of theta. Now, we can use this to derive a formula for dy, the derivative of y with respect to x. I prefer not to use that formula in general, although it is useful in proving this result up here. Dy over dx can be found by taking the derivative of this piece and the derivative of this piece, and then just dividing. Well, this is a product, so if I want to take the derivative of this with respect to theta, I just use the product rule. So according to the product rule, this is what we get. Derivative of the first, it's not a vector, sorry. Derivative of the first times the second, undifferentiated, plus derivative of the second, which is cosine of theta, times the first, undifferentiated. And then we divide by derivative of the first times the second, plus derivative of the second, which is negative sine of theta, times the first. And I did not stick to my color convention. That's okay. All right. So we're saying dy dx can be written this way if we want to. I generally don't use this, but I could use this if I wanted to. Once I have r, I could find r prime of theta and r of theta, and I could substitute it into this formula, and that would give me dy dx as a function of theta. Now this is what, we've got a fact here. It says, if r of theta naught is 0, and r prime of theta naught is non-zero, then theta equals, theta naught is tangent to the graph at the pole. Now let's see. Let's evaluate this at theta equals theta naught, where theta naught is a particular value. Well, if r of theta naught is 0, those two terms are gone. So we have r prime of theta naught times sine of theta naught over r prime of theta naught times cosine of theta naught. And then I have a 0 here and a 0 here. Now, if these are not 0, they're just constants, so they reduce. And I have sine over cosine with the same angle. So dy dx, that's the slope at the pole, is given to tangent of theta naught. Well, the slope is equal to the tangent of theta naught when theta, when y is equal to, or y over x is equal to tangent of theta naught. Which means that y is equal to tangent of theta naught times x. And that is equivalent to the equation in polar coordinates, theta equals theta naught. So if this is 0, so this is gone, and this is non-zero, so it's just a number divided by itself and it cancels, the derivative of y with respect to x at theta naught is equal to this tangent. And that corresponds to, now we're saying that the slope of the tangent line at that point is equal to this. Well, if the slope of the tangent line is equal to this and it passes through the origin because r of theta naught equals 0, we're saying that y over x is tangent of theta naught, so y is equal to tangent of theta naught times x. And the equivalent form of this equation, or this equation in polar coordinates, is theta equals theta naught. So that is going to be tangent to the graph, and that might help us graph a little bit. Let's see if we have any of those points for this function that we found earlier. Excuse me. So let's say we've got r of theta equals 1 minus sine of theta. And we want r prime of theta. We want to calculate r prime of theta. Derivative of r with respect to theta is negative cosine of theta. Well, this is 0. If we set this equal to 0, this is 0 whenever sine of theta equals 1. And that happens at all of the multiples of pi over 2. Or not multiples of pi over 2, excuse me. It happens at pi over 2 plus all of the multiples of 2 pi. So r of theta will be 0 whenever we're at this angle. Theta equals pi over 2 plus 2 pi. 2 pi n as many times, you can add and subtract 2 pi as many times as you want. Okay, now at those points, the cosine, oh, is cosine equal to 0 there? Yeah, I think we do have a problem. R prime at pi over 2 plus 2 pi n, that's negative cosine of pi over 2 plus 2 pi n. Well, that is 0. So r of theta is equal to 0 at these angles. Well, at the same angles, that derivative of r with respect to theta is also 0. So it looks like we don't have any tangent lines that pass through at the pole for this particular function. That's okay. This still holds for other curves. Let me show you one from the book, just briefly. This is from the Larson and Edwards Calculus book with Early Transcendental, 7th edition. So here's one with some tangent lines that go through the pole. So if r is equal to 2 times cosine of 3 theta, we end up with this little flower shape. And this function is equal to 0 whenever 3 theta is equal to a multiple of pi over 2. So we've got, well, that ends up happening, ends up happening quite a few times. Anyway, we won't start a problem from scratch on that. So let's go back to the original, the beginning of the video. What were we trying to do? Well, I wanted to graph r equals 1 minus sine of theta. This is the method. We graph r in the r theta plane. We calculate the increment, come up with a table of values, and then we plot the points. And then once we had our plot, we were able to visualize all of this by graphing these points on our graph and then noticing that the slope of the tangent line was, or the slope of the tangent line was horizontal at the supposed points of horizontal tangency, so that's good. And the slope of the tangent line seemed to be, or the slope of the tangent line was undefined. We had vertical tangents at the supposed points of vertical tangency. Not perfect because our graph isn't perfect, but we can see that there's probably vertical tangents there. We can imagine that if our graph was perfect, those tangent lines would be vertical. And then over here at pi over 4, we said the slope is supposed to be 0.4. When we graph that point at pi over 4, we see there's a small positive slope. So yeah, that sounds about right. The last thing we talked about is this. If the function value at a particular value of theta is 0, and the derivative of r is not a vector, I'm sorry, I'm thinking about calculus 3. The derivative of r with respect to theta at theta naught is not equal to 0, then theta equals theta naught is tangent to the graph at the pole. So you might have one of those flower cases. Maybe the graph looks like this. Well, all the petals should be the same size. But you would end up with these lines that sort of cross like that. Not a great picture, but I hope you get the idea.